What is up, everyone, and welcome back to the base unit. In this episode, we're going to be talking about scalars and vectors. These are two categories in which quantities fall into. So they can either be scalars or they can be vectors. And the difference between them is that scalars have no direction while vectors have a magnitude and a direction. So for example, if that makes no sense to you right now, what we can say is that if there is a cheetah, I say the speed of the cheetah is 100 kilometers per hour. Now that could be in any direction. I haven't told you whether it's going to the left, to the right, forward, backwards, right at you. We don't know which direction the cheetah is running in. If I choose to mention a direction, then I have to change my terminology. I cannot say that the speed of the cheetah is 100 kilometers per hour and in this direction. Then I have to say velocity, because velocity is associated with direction while speed is not. Now another example of scalars and vectors is with distance and displacement. So distance is a scalar and its vector equivalent is displacement. Say for example, I have Messi. He's training on his own and he's set up 4 markers in a square. So he's got marker 1, and 30 meters from marker 1 is marker 2, and from marker 2 there's marker 3, and from marker 3 there's marker 4, and each marker is 30 meters away. So when he runs from marker 1 to marker 2, he runs 30 meters, and when he comes back around all the markers back to marker 1, he's moved a distance of 120 meters. So that would be his distance. That's a scalar quantity. But his displacement would be 0. It would be 0 because he's back to where he started. When he moved forward, and he moved back as well. So 30 minus 30, that's 0 in the vertical axis. And when he moved to the right, he moved 30 meters to the right, and then he has to move 30 meters to the left. So 30 minus 30 again is 0. So we break down both horizontal and vertical motion, and overall we get 0 and 0, like coordinates on a map. He ends up back to where he was. So that's what displacement is. Where distance we had 120 meters, we've got 0 meters in terms of displacement. And so here are some of the quantities that you need to know and the category that they fall under. Some of them are scalars, some of them are vectors. And I also have a more comprehensive list in the description for you to look at for which ones are scalars and which ones are vectors. And with that, I've got all the definitions for the quantities. So please check those out, because you will also need to know definitions, because some questions do ask you what the definitions are. And the definition can also help you to solve some questions, because the definition sometimes represents the formula. In many cases, it represents the formula. So what we're going to do now is we're going to talk about adding and subtracting vectors. Now, you already kind of looked at that already when we talked about displacement. When Messi moved up, he moved plus 30 meters, and when he moved back, he moved minus 30 meters. So vectors come with polarities. If in one direction we have positive, then in the opposite direction we have negative values. So what we're going to do is we're going to add or subtract vectors in the same line of action. We previously added vertical vectors together, and then we added horizontal vectors together separately. So we have to look at them on an individual basis in their own line of action. For example, I've got 5 meters per second as a velocity towards the right. Then I also have 3 meters per second as another velocity towards the right. If I want to add these together, I would get 8 meters per second as a velocity to the right. Now, if you look at the arrows, the 5 meters per second arrow is greater or bigger than the 3 meters per second arrow. because when we represent vectors in terms of arrows, then the size of the arrow determines the magnitude. We're looking at bigger vectors if the arrow is bigger. So if I had 5 meters per second towards the right, and this time I had -3 meters per second towards the left, then I would end up with a smaller vector which was 2 meters per second, and you can see that the size is smaller because the magnitude is smaller. Many times when we are representing vectors, we use a scale diagram. So say there's a batsman and he hits a cricket ball
tight.
With a certain amount of force in a certain direction. So I could use a scale and say that 1 centimeter is equal to 1,000 newtons. Now, if he uses a force of 6,500 newtons or 6,500 newtons, so that means on the diagram, the length of the arrow will be 6.5 centimeters. So we can use a scale to represent the size of the vector. We can also add vectors that are not in the same line of action. So if I had a vector towards the right which was 4 meters per second, and there was a vector moving up from that point as well which was 3 meters per second, I can combine these first by using what we call head to tail rule. And what I do is I take the tail of one of the vectors and I move the arrow over to the head of the other, and then I can draw a line from the end to the tip of the other vector, and this would represent the resultant vector, the combination of both of these vectors. Now, the resultant can be calculated by using Pythagoras, because you can see that we've made a triangle. So in this case, when I find out what the resultant is, it turns out to be 5 meters per second. And you can see that there's an angle theta, so we can use Pythagoras to find out what this angle theta is as well. We have all three sides, so I can use sine, cos, or tan. So let's say, for example, I use cos. Now, cos theta is adjacent over hypotenuse. So 4 over 5 will give me cos theta. When I inverse cos theta, I end up with 36.9 degrees, and that's the angle that we have with the horizontal. Okay, so what if the vectors are not at right angles to each other? What if they have maybe, let's say, a 60-degree angle between them? So I can start off by doing the same thing, which is the head to tail rule, and I can take the tail of one of the vectors and place it on the head of the other one, and then draw a line to connect them again, and that would be my result. Now, since I don't have a right angle triangle, I'm going to use cosine rule to find out what my resultant is, and in this case it's 10.4 newtons. So now that I know what the resultant is, I can also find out what the angles are within the triangle. Now, the angle at the bottom, I can use sine rule to find out what this angle is, and when I calculate the angle, it turns out to be 24.6 degrees as the angle with the vertical. Now, another concept that you have to understand when it comes to vectors is known as a closed triangle. So say, for example, I have two weights that are hanging on pulleys. Now, one of the weights is balancing the other one, so they're in some kind of equilibrium. Now, if I take one more string and hang another weight down the middle, then I have three weights, and you can see that the whole system adjusts itself to find a new equilibrium. So now I have three forces acting on this point in the middle. So they're all acting because of the three different weights that we have. We've got tension 1 for the weight on the left, tension 2 for the weight on the right, and W for the weight in the middle hanging downwards. Now, if I use head to tail rule for all three of these, I can create what is called a closed triangle, and you can see that all three of these arrows move around in the same direction, either clockwise or anti-clockwise. This is a condition for equilibrium. So three forces are in equilibrium, which is known as a closed triangle. So now that we have combined vectors, we can also take them apart. We've got a resultant vector which we can break down into its horizontal component and its vertical component. So the way we do that is we use Pythagoras again. So here I have a resultant vector, and you can see that there's an angle with the horizontal theta that I have. So now what I can do is I can find out what the horizontal component is and the vertical component is. So when you look at the horizontal and vertical components, I can create that triangle again, and that angle here we have on the left. So if you look at the side that's opposite to the angle, that is the vertical side. Now that vertical side can be found using sine theta, because sine theta is opposite over hypotenuse. In this case, hypotenuse is the resultant. So if I rearrange this equation, I end up with r sine theta is equal to the opposite side. And similarly, the adjacent side is equal to r cos theta. So we've got r sine theta and r cos theta. So in this way, we've taken our resultant vector and we've split it up into its horizontal and vertical components. Now, why do we need to split up a resultant vector into its two components? The reason is that in order to combine multiple vectors, we have to split them up into horizontal and vertical components, add all those horizontal components together, and then look at all the vertical components and add them all together, and I can get one total value for the horizontal components and get one total value for the vertical components. Once I have the total horizontal value and the total vertical value, then I can combine those again and find my total resultant, which is a combination of all the resultants. And then using the total horizontal and vertical value and the resultant, I can then find the angle of this overall resultant, basically the direction in which it will be acting. So that's about it for scalars and vectors. In the next video, we'll be looking at errors and uncertainties. So I'll see you then, and